welcome to the lecture on design via root locus and compensation techniques. So in the previous lecture we discussed about PI controller design. In this lecture we will discuss one example based on PI controller design as well as the PD controller design, that is proportional plus derivative controller. So here we say that the PI controller, that is, have two parts, proportional plus integral, and how with these two parts we can get the equivalent transfer function for this PI compensator. Now we take one example for this. So we can have, let's take the example. So we have this system. Here is the gain k. So here we are giving the step input. So we want that this is the system, and we can see that here there is no any, in this system there is no any pole at origin because there is no any S. So this is type 0 system, and this type 0 system is subjected to step input. So Rs equal to 1 by S. Now we want to design this system for 0 steady state error, and at the same time we want that the transient response of the system remains for damping equal to 0.174 line. So we want that the system is designed for steady state retaining the transient response corresponding to damping equal to 0.174. So we know that this cos theta, and so theta equal to cos inverse 0.174, and we can get so here if we plot the root locus for uncompensated system, so this is sigma j omega, we have -1, -2, and let's have -10, and this is theta equal to 79.98 from here. So we will have, this is the line, that is zeta equal to 0.174, and this angle is 79.98. So we have a root locus will start from the poles and it will go to cross this line at some point, and we get that. So we know that how to find this point that intersect some particular damping line, and so this point we can find with the condition that if this point, we can select some points on this line, and the point that satisfies the angle condition, that is the angle is odd multiple of 2k plus 1 180, or odd multiple of 180 degrees. So that point is on the root locus as well as on this line. So we find this point is, we can find this point as 0.0 0.694 plus J 3.92. So here we are getting this point 0.694 plus 3.926 J, and similarly the other point will be here, that is with minus J 3.926, and the third point we will get here, and that is minus 11.61, and we are getting gain for which this point is on this damping line. This K is 164.6. So this is the uncompensated system where we are getting this point on this damping line that satisfied these transient response conditions. So this point, let's say A. Now we want we want to know that what is the steady state error at this point. So steady state error here is, so we first calculate Kp equal to limit Gs s tends to 0. So we will get, this is Gs is this complete system. So K upon 1 into 2 into 10, because S is 0. So and K is 164.6 by 20. So we are getting it as 8.23. So we are getting Kp as 8.23. Now we can find the E infinite, that is the steady state error, that is 1 by Kp. So 1 by 8.23, and 1 by 1 plus Kp. So here equal to 0.108. So this is the steady state error currently. So there is some finite error in the system. Now if we want to design a compensator in spite of just a gain, so that the steady state error is 0, so let's take one compensator. So we have here, we can have in this circuit, we can have a compensator. So let's have K upon S, so one pole, and we put some 0 close to the pole, that is 0.1. So because this pole is at origin and we put at 0.1 close to this, so that now the system type is increased, because this complete transfer function will have one pole at origin. So the system type is increased, and therefore when we have one S here, this 0 will keep Kp infinite, and Kp infinite will keep this steady state to tends to 0. So we will get this steady state. Now what happens to root locus? So we have this point. So here is -1, -2, and here is -10. Now we have one pole here at origin, and there is at 1 0 at 0.1. So this root locus will start and end to this 0. This will start here, and this will go to this point. So the root locus will, and this is the zeta equal to 0.174 line, and the root locus is going to cut this line. Let's say this is point B, and we can find this point B, and we will get that it is minus 0.678 plus J 83.837. So it is cutting this point here, and gain is 158.2, and similarly here the second point is here, and third point here, and so on. So we are getting that here Ts equal to 4 upon sigma d, and we see that here we have sigma d earlier uncompensated system. This we have got, the steady state 0 we have got by putting one pole at origin, but due to the effect of this 0 we will get a very small change in the tangent response characteristics. So we see that here it was 0.694, now it is 0.678. So sigma d at B is greater than less than sigma d at A, this point 0.678. So Ts B is greater than Ts A. So we can see that we will have the faster response. So settling time is increased with the same percentage overshoot. So here percentage overshoot is same, but settling time is increased, and so here we see that there is minor increase in the settling time, and so we are able to keep this transient response closer to the earlier one. So it is, we can say, without much affecting or less, with less affecting this settling time, we have found the steady state 0. So we have designed this system. Now we come to another system, that is the PD controller. So here we can, in this diagram we can see the response of the two systems. So this is uncompensated system, and we can see that uncompensated system is, of course, there is this is the transient response characteristics, but steady state error is large. However, with ideal integral compensation we have improved the steady state error, because steady state error is tending to 0, and at the same time we see that settling time is larger. So here it settles earlier, but now we are seeing that the settling time is increased for this system. So we have got larger settling time. Now we come to the ideal derivative compensator. So ideal derivative compensator we used to improve the transient response, because the PI controller we used to improve the steady state error. Now this ideal derivative compensation technique we use to improve the transient response. So we want to find some desirable percentage overshoot and a shorter settling time than the original system. So it means we want to improve the transient response, we want fast response, because we want shorter settling time. So this we can do by choosing an appropriate closed loop pole location on the S plane. So if we want to improve the transient response, we can select a point on the root locus or on the S plane, so that we can get the desired transient response. However, if the point that is giving the desired transient response is not on the root locus, then we need to use this PD controller. If it is under root locus, then simple gain we can obtain some value of gain that will give that response. But if it is not on the root locus, so we have to augment a PD controller or PD compensator to the system, and that to obtain the desired transient response. So in this case we add a single 0 to the forward path. So ideal PD controller, we can see it is similar to, so here we say that we are going to add a 0 to this plant now. This PD controller is proportional plus derivative. So we have this RS, here is proportional part, let us say that is K1, and then here is the derivative part. And here is the GS, and here is CS, and derivative means we have K2 into S. So Laplace transform of a derivative. So we have a derivative. So d by dt function. So the Laplace transform is K2S. So in time domain it is derivative d by dt, but in S domain it is K2S. So now if we want to find GCS, so we have K1 plus K2S. So this is the transfer function. Now we can have K2 S plus K1 by K2. So K1 by K2 will help to select the location of the 0, that is ZC, and that is equal to the, so K1 by K2 is equal to ZC if we compare here, and K2 is equal to K. So K2 is selected as the gain proportional. So here K, corresponding K is K2, and K1 by K2 is ZC. So we can get K1 and K2, and we can get this PD controller circuit. So now let's take one example for PD controller. So we have a system here. So RS So we have this system, and this system we have to this is an uncompensated system, and we have a transient response corresponding to the damping equal to 0.4 line. So we want to keep the percentage overshoot or damping corresponding to this line. At the same time, we want to reduce the settling time. So, we want to improve the speed of the response. So, faster response we want. So, here we can see the settling time is 4 upon zeta omega n, and therefore, if we want to improve this settling time, however, percentage overshoot is function of the damping, and so the damping will be constant if we want to move with 0.4 line. So, if we plot the root locus for this system, we can see here so here -1, -2 and -5. There is no any, all the zeros are at infinite open loop zeros. So, we have this root locus, and we have this is a line corresponding to zeta equal to 0.4. This is a line, and from this angle from here is 3.6 degree. So, now the root locus that will pass here, and it will pass through this path, and it is going to cut here at point A, and this point A is minus 0.939 plus J 2.151, and the gain K we are getting is 23.72. So, in this diagram we can see here we have this pole -1, -2 and -5, and the third this corresponding to K equal to 23.72, we are getting the location of these closed loop poles as -0.939 plus minus J 2.151, and the third pole is at this location beyond -6. And this line uncompensated, this is showing the response of this system, this line, black line, uncompensated response. Now, we want to, because if we want to have a PD controller, we have to add here 0. So, here it should be K S plus ZC. This is the compensator, PD compensator. We are going to add 0. So, let us we try 3 conditions. We add and check whether we are adding 0 at -2, -3 and -4. So, we are adding this ZC is 2, 3 and 4. So, ZC S plus 2, so we are getting S equal to -2 here, this 0. So, first condition is we are going to add a 0 at this location itself. So, here this root locus we can plot sigma. We are going to add here, so this is -1, -2 and -5, and we are going to add here 1 0 at -2. So, we can see the root locus will be here, it will start and end to this 0, end to this 0, and root locus will start here, it will start here, and here is this zeta equal to 0.4 line. And so this line will cut here to this line somewhere, some point it will cut, let us say B. And so here we can see that at 0 is minus 2, this line is going to cut zeta equal to 0.4, this root locus is cutting at minus 3 plus j 6.87, minus 3 plus j 6.87 at k equal to 51.25. So here what we have done, because this point we can see earlier it was minus 0.939, now it is 2.1 and plus j 2.15. Now on the real axis part is increased, so it is now minus 3. So the settling time, because this real part is increased, the settling time will decrease, the response will be faster. Now come to the next one, that is we are adding this 0 at minus 3. So we are now taking this part. So we are adding this at minus 3, and we can see when we are adding 0 at minus 3, the root locus will always form at the left of the odd number of poles are 0. So it will be here, so and it will be here. So we can see this locus starting at these poles and going like this. The other part start here and ends here, this part, third. So here it is cutting this damping line at minus 2.437. So again this real part is more than the uncompensated system. So in this case also the settling time is improved. Now come to the compensated 0 at minus 4, when we are putting here at minus 4, again this root locus cutting at minus 1.869, that is almost double of this real part of uncompensated system, and here also the settling time will improve. So now we can see the responses of these three, and we see that here this is percent overshoot is constant, we have keep constant percent overshoot, and the more negative real and imaginary parts smaller will be Ts and Tp. So because here Ts is 4 by sigma d, that is real part, and peak time Tp is pi by omega d, that is imaginary part. So if they are larger than the uncompensated system, the corresponding Ts and Tp will be smaller, and so the response will be faster. So here we can see that in compared to uncompensated system, for all these three zeros that we have selected or compensated schemes, we have retained the same percent overshoot because the damping line is constant. All these points are on this damping equal to 0.4. So percentage overshoot is the same. However, we can see that at 0 at minus 2, we have faster response than at minus 3 and then at minus 4. We are getting fast the peak time less in case of 0 at minus 2. So this we can understand from this table. This is uncompensated systems transfer function, and this is compensated with 0 at minus 2, and this is compensated 0 at minus 3, compensated 0 at minus 4. We are getting the dominant poles corresponding to the gains that are passing through the damping line zeta equal to 0.4 and percentage overshoot 25.38. We are getting here the natural frequency changing this system. So earlier uncompensated system has this natural frequency, now we have these and we are getting settling time. Here we are getting 4.26. In all these three cases we are getting a great reduction in the settling time. Here 1.33, here so almost one third, here 1.64, and here 2.14. so this is almost half settling time. Similarly, we are getting reduction in peak time. So here 1.46, but here only 0.46, 0.56, 0.73. And here we can see that Kp we have calculated, because this is a zero type system, so this position static error constant is valid. So we are getting these values. Now if we see the steady state error, here it was 0.297, but here it is 0.089, 0.086 and 0.107. So we see that while our target was to improve the transient response using PD controller, but at the same time we were able to also improve the steady state error. But this may not be always the case. It could be also that the steady state error could be badly affected by improving the transient response. But in these cases the steady state error is improved, and we see that here second order approximation is okay, because the third pole here is minus at -6 in compared to this real part is -0.9. So 5 times far if the pole third pole is than the dominant pole's real part, then we can approximate as a second order system. So here it is more than that, so here we can have second order approximation. But in this case we can see that this pole 0 will be cancelled, so it is a perfectly second order system. Now here again it is -2.4, and here 0 is at -3, say at third pole is -3. So in this case I think there should not be the proper this approximation, we can't take. Now we come to this ideal compensation, ideal derivative compensation drawback. There is some drawback of this ideal derivative compensation. We can have this ideal derivative compensation requires an active circuit to perform the differentiation, and differentiation is a noisy process, and the level of the noise is low but the frequency of the noise is high. Therefore differentiation of high frequencies can lead to large unwanted signals. Therefore to get this drawback we need to use the lead compensator, that is a passive systems, and so therefore we will also discuss the lead compensator to overcome the disadvantages of the PD controller in next lectures. So these examples were taken from the Norman S. Nice Control Systems Engineering reference book, and I thank you for attending the lecture and see you in the next lecture.